So, in today's class we will look at some aspects of transient conduction. As you all know, transient conduction is a very important topic in conduction heat transfer. So, in the last few classes we have been looking at the steady state temperature of systems, right, whether it is a spherical tank storing liquid oxygen, or there is a brick wall, or there is a material with variable thermal conductivity, or there is a nuclear fuel rod. Though it is generating heat, heat is being taken away, we are looking at steady state. We are not looking at transients. What happens when the nuclear fuel rod is generating heat but enough cooling is not available? What will be the temperature response of the nuclear fuel rod? These are also important, right? All the time we cannot expect system to be operating at steady state. There will be a startup phase, there will be a shutdown. Transients are the norm. Generally you can see transients around, but basically if you look at issue, basically if you look at a complex power plant and all that, we are interested only in the steady state operation. That is fine, but there are startup and shutdown of even for a data center, laptop computer, cell phone, or your nuclear power plant. These are all critical. Nuclear power plant, for example, you know that the startup and shutdown are extremely critical. So, the most complicated could be 3-dimensional unsteady, could be the 3-dimensional unsteady conduction. You know that we cannot solve it on the blackboard and all that. So, we have to use a separation of variables and all that. It will involve a lot of mathematics, and also if it is 3-dimensional unsteady in spherical or cylindrical coordinates, it is going to be very messy. So, we will restrict our attention to Cartesian coordinates. We will start with a simple 1-dimensional transient conduction, but if it is 1-dimensional, t is already a function of x. I am also saying that it is transient, therefore t is a function of time, therefore already temperature is a function of more than one variable. So, temperature will be a function of two variables even in the simplest case, but the two variables will not be the spatial coordinates. One will be the spatial coordinate, one will be the time coordinate. Let us consider a simple case like that, right. Now, okay. So, the governing equation let us consider the situation in which QB equal to 0. I say that t is a function of t and x only, right. Therefore, I can say the governing equation even though t is a function only of x, I am constrained to put dou square t by dou x squared because t is a function of time also, alright. So, let us call this 1. We can rewrite this as okay. So, what should be the units of this alpha? Okay, I wrote out the units of for K thermal conductivity, rho density, and Cp specific heat. Deepak, any problem? I will cut the kg and cut the Kelvin. So, I have meter square, and what is joules per second? So, I have So, alpha is called the thermal diffusivity. This alpha makes its appearance only in transient conduction problems. So, in transient conduction problems, it is not the K which is the supreme property which is responsible for all the mischief. In steady state conduction, the fin, when we change from aluminum to copper or copper to stainless steel, you saw that the performance will change, because m squared is equal to hp by k, everything will change. Steady state conduction, thermal conductivity is king, but in unsteady it is thermal conductivity divided by rho into Cp, which has got the units of meter square per second. So, it gives you a rate at which the thermal disturbance propagates. So, we will look at the physical interpretation of alpha a little later, but now it suffices to say that the alpha is a parameter, is a quantity, the physical is a thermophysical property which appears in the transient conduction equation, right. Alpha is a property of the material. Alpha for wood is different from alpha for steel, alpha for steel is different from alpha for aluminum, copper and all that. So, if you are looking at some unsteady heat transfer and you want a design based on that, then you will choose your material appropriately. Mathematicians refer to this equation as the heat equation. Why did they call this heat equation? Because this is one of the important equations they considered when they developed solutions, analytical solutions, by using the method of separation of variables. So, mathematicians use this equation, they will use wave equation, heat equation. So, when they say heat equation, they mean this, okay. So, alpha is a property of the medium and it changes. Now, there are several ways of attacking this. I can assume a product solution that T is a function of a solution which is a function of only x multiplied by another solution which is a function only of T, start writing dou by dou on dou squared everything and convert it into, and then write the general solution, then put the boundary conditions, and that is one way of looking at it. But I thought I would because of the limited time, if you get into that method of separation of variables, these two classes will just go off. So, I thought we will use a different, we will adopt a different tactic, where we will go into the equation in depth and try to arrive at some meaningful understanding of these equations by looking at either the non-dimensionalization or by looking at the scaling parameters and so on, only for a very simplified case where T is a function only of time, which is called the lumped capacitance method. We will get the solution and work out a problem, okay. Now, let us look at let us try to get some insights into this problem by considering a situation where I have a slab like this, it is infinite in extent, okay. So, this is L and x starts from here. This slab is at a temperature of T equal to Ti. This slab is at a temperature of T equal to Ti at time T equal to 0, okay. Suddenly at time T equal to 0, this body is pushed or immersed in a cold fluid which gives a heat transfer coefficient of H, and there is a free stream temperature of T infinity. Do not be under the impression that at x equal to L and x equal to minus L temperature is equal to T infinity, that is a separate story. Unless the heat transfer coefficient is infinity, that will not happen. Now, there is a hot chalk piece, I am putting it in cold water or cold oil, the chalk piece will dissolve on, I mean that is a don't let us not get into that. Now, this body remains, now it is undergoing cooling. Now, as a heat transfer engineer, at any point in the solid, inside the solid, if I tell the point and the time, you should tell me the temperature, that is the goal. This knowledge, this cannot be answered by thermodynamics does not do, because it is equilibrium. It will say after everything is over, it will say chalk piece will come to equilibrium with that. the heat from the chalk piece will go into the water. What is the equilibrium temperature of water and chalk piece? Thermodynamics will tell you, but we have no patience. We want to do heat treatment of this, we want to pull this out after 20 minutes and do some other cooling and all that. Therefore, we need to know at a particular instant of time at a particular place what is the temperature. That is why we are doing all this. Okay. Now, the story is clear, then I have to tell that Ti is greater than T infinity. So, the slab is cooled, right, and you have symmetric boundary conditions on both sides. Okay. Now, let us start working on the equation. This equation is first order in time and second order in x. So, you require, it supports two boundary conditions in x, right. It is first order in time, it supports one condition in time. The condition in time is called the initial condition, because normally in these problems we will know what is the condition when you start. At t equal to 0, what is the story? At t greater than 0, at 2 points in x, you should tell the temperature or the information about the derivative of temperature, or how the derivative of temperature is related to a flux or something. That is there could be a convective flux or a radiative flux or a convective plus radiative flux. Okay. So, the initial condition how will mathematicians write for all x? Is it correct? Somebody will start, some people may start shivering when you use that symbol, but we can as well write for all x. Okay, fine. Now, boundary conditions. 1. Tell me. Why?
Symmetric.
It is symmetric, right? And you expect the temperature to be maximum at the center. Why? Hot chalk piece is put in cold water. The center of the chalk piece, for this coldness to penetrate the center, it will take a long time. First the outer surface will get disturbed, then the layers will start getting disturbed progressively. Now, so x equal to 0, dt by dx equal to 0. What is the second boundary?
Convective boundary.
Yes. What is that? X equal to L or plus minus L, correct. Is that okay? So, this is 3, this is 4. Now 3 to 6 is called the governing equation plus initial condition plus boundary condition. After you give 3 to 6, mathematician is enough, heat transfer engineer is not required, right. So, it is just for them, it is a partial differential equation, they will try to solve it, right. So, once you write one initial condition, two boundary conditions and the governing equation, we say it is mathematically closed, CLOICD, that is it satisfies that closure. It requires all the information, you have all the information required to solve the problem. Now, I am still trying to dodge by not solving, right. So, we are trying to get some physical interpretations. Now, let us try to do some non-dimensionalization or normalization of the equations, right. So, I defined a new dimensionless temperature or dimensionless temperature excess, which I call it as T minus T infinity by Ti minus T. What is the funda behind this? What will be the minimum and maximum values of this phi? Correct. So, 0 less than equal. So, when I write a computer program, if all the temperatures are varying between 0 and 1, it is very good for me. Double precision, maximum information I can retain. otherwise if I have 300 point something, some 2 or 3 digits I am already losing, okay, fine. Now xi equal to x by L. So what are the values of xi in this problem? Correct? X we have done, this we have done. Now I define what is called the Fourier number. It is a product of the thermal diffusivity multiplied by time divided by L square. When I write it like that, alpha is meter square per second, time is second, so meter square by meter square, Fourier number is dimensionless. So it is yet another dimensionless number in heat transfer. So Joseph Fourier worked on it, so we want to honor him, and so we have put this as Fourier number. What is this Fourier number? Fourier number is nothing but the dimensionless time. So time, is it okay? So L square by alpha is a time scale for the problem. L square by alpha is a time scale for the problem. Therefore, if you divide T by L square by alpha, you will get something which is dimensionless, but which is indicative of the temperature, because L and alpha are already fixed. For the chalk piece, you know what is alpha, you know the dimension, so only the T is changing. So it gives you information on the time. Okay. Now with this we will now normalize or non-dimensionalize the governing equations. So the governing equation is basically from T I have to go to phi, okay. So this will be just is that correct? Yeah, please check whether it is all right. D of t and d of t minus t infinity is the same, because d of t infinity is 0, okay. When you are taking the differential, you can subtract, add, whatever, so long as the other one is a constant, okay. So what has this equation become now? So this is 7, 8, 9, this is again the same thing, 10, therefore the governing equation has become like this. What about initial condition? Time equal to 0 means Fourier number equal to 0, phi equal to 1, phi equal 1. Now boundary condition, is it okay? So we can knock off these fellows. What another board? Yeah, we will do that. So this one is xi equal to plus or minus 1, Yeah, Vikram, what is that? Xi equal to 0. Okay, so is that correct? Now this HL by K is called the Biot number. Okay, so this HL by K why am I writing like this? When we solve the one dimensional steady state conduction equation for the wall, what was L by K? Resistance. 1 by H resistance. L by K is the resistance for conduction. 1 by H is the resistance for, therefore HL by K is actually the conduction resistance by convection resistance. Okay, now we will take a detour for a few minutes and then we will come back. Yeah. Now we will take a short detour for a few minutes to get this concept better. Let us take this. Let us take this example where we have H1 T infinity 1. Okay, this T1 and this T2. This some other solid with L1, right? So what did we do here? So we said H1 into is it correct? Now correct, you must put a title for this, you should not get confused with the transient conduction. I am doing something else here. Okay, so T1 minus T2 therefore if the Biot number is very small, which could mean that the thermal conductivity of the wall is very high, the Biot number is very small, therefore the right hand side is negligibly small, therefore T1 minus T2 will be very gentle. If the thermal conductivity is very poor, to accomplish the same heat transfer rate is very poor, the Biot number is very high, therefore T1 minus T2 will be substantial. Okay, therefore, so the Biot number lets us decide whether there are temperature gradients within the solid. If the Biot number is very small, therefore we are at liberty to assume that the whole solid is at one temperature, which is called the lumped formulation or lumped capacitance method. Granted, no heat transfer will take place without a temperature gradient, but for a finite flux Q is equal to Ka dt by dx. The K is so high that for a finite Q dt by dx is negligibly small in relation to what? In relation to the temperature drop which is required for accomplishing the convective heat transfer from the stream of the fluid to the solid. So compared to T infinity 1 minus T1, T1 minus T2 is substantially small, therefore in relation to this we need not worry about this. Therefore if you have a situation where Biot number is much less than 1, then this system is dominated completely by the surface resistance or the convection resistance which happens at the interface between the solid and the fluid. On the other hand, if you have a situation where you have a plastic or an extremely poor conductor, then given that you have a situation where there is a conduction and convection coupling or conjugate heat transfer which is taking place, the controlling resistance will be the large conduction resistance or the poor conductivity of the solid under question. Therefore you cannot ignore the gradients within the medium. Is that okay? So Therefore, Biot number less than 0.1 T okay. So, if I give you a transient conduction, if you encounter a transient conduction problem, the first step is to calculate the Biot number. If the Biot number is less than 0.1, you can go ahead and convert it into a problem where there is only one temperature within the whole solid. Okay. Now, this Biot number is HL by K, in this case H was clear, otherwise you have what is called HLC by K, okay. LC is the characteristic length. Equal to V by A. I hope you get L, I hope you do not get 2L in this problem if you do V by A, okay. So, if it is a sphere 4 by 3 pi r cube divided by 4 pi r squared, LC will be r by 3. So, take the radius, calculate r by 3, get the thermal conductivity of the sphere, heat transfer coefficient will be given to you, calculate HL by K. If it is greater than 0.1, then lumped capacitance will not work. If it is less than 0.1, then you can use the lumped capacitance. What is this lumped capacitance? We will talk about it a little later. So, this is to explain the concept of Biot number. What it means is, what it now means is, you have a xi, you have a Biot number, you have a Fourier number. Therefore, phi is a function of xi Biot number. So, this is the result we got by doing a normalization or non-dimensionalization of the governing equations. This is considered as standard practice in fluid mechanics and heat transfer. There is yet another way of getting these 3 parameters. What is that method? You can use the Buckingham Pi theorem. You can use the Buckingham Pi theorem and get the same thing. However, it is easier to do it with non-dimensionalization also. So, the temperature, dimensionless temperature will be a function of the dimensionless distance. That is the way it should be, because this gives the conduction convection coupling, this gives the time, and this gives the space. So, temperature is a function of the spatial coordinate, the time coordinate, and the coupling between the conduction and convection, okay. Then these equations have to be mathematically solved and all that, but now let us look at the physical interpretation of this. What is actually happening in the transient conduction? Okay. So, this is the slab, I am looking at the temperature levels. Initially T equal to Ti everywhere, correct. After everything is completed, what will be the temperature everywhere? T equal to T infinity, okay. Therefore, this delta T, Ti minus T infinity is the maximum temperature difference in the problem. All the temperatures have to lie between Ti and T infinity, agreed. Now, initially you have T equal to Ti, then what will happen is, after some time the system will behave like this. After some time this correct. So, what is this? There are 3 regimes. There are 3 regimes for the conduction, transient conduction. There is an initial regime where there is a portion of the slab which does not know that there is a disturbance which has taken place at x equal to plus L and x equal to minus L. So that is the early regime. There is a middle regime in which at all points in the domain the effect of the disturbance at the wall is felt, that is this temperature is coming down, this temperature is coming down, of course the temperatures are coming down at different rates depending upon the governing equation, what the equation tells you, right, that is called the middle regime. Then we have a late regime. Watch the late regime. In the late regime the temperatures have already become very small, all the temperatures are tending to approach T infinity, therefore the gradients within the medium are also very small. This is what corresponds to Biot number much less than 0.1. So that is the late regime case. Okay. So simplifications are possible in regime 1 and regime 3. Simplifications are possible in regime 1 because all the solid is not taking part in the heat transfer activity. In regime 3 the complete solid is taking part in the heat transfer activity, but the gradients of temperatures are very small because the body itself is sluggishly approaching towards T infinity, therefore you do not worry about the temperature gradients within the body. Therefore simplifications are possible to the governing equation in regimes 1 and regimes 3, but in regime 2 you have to solve the full transient conduction equation. Okay. Let us look at the early regime now. Okay, so after some time the temperature is, this is T equal to 0, this is T equal to T1. Okay. What about this region? This region which I have enclosed by the two arrows is completely ignorant of the presence of a disturbance, that is some cooling has taken place at x equal to plus or minus L. Okay. This region, this is the region where the effect of the disturbance is felt. Therefore, at a particular time t is equal to T1, if we try to find out this region where the thermal disturbance is felt and this thickness, if we call it as delta, that is the penetration depth, that is the depth of penetration of the thermal disturbance from the surface. How does this penetration depth go? How does it scale as? Okay. Are there some, can we know more about this delta? So for this we have to do what is called scaling analysis. What is the scaling analysis? The governing equation is replaced by approximate terms. Okay. So I say what is a good scale for delta T in the problem? Maximum delta T, what is Ti minus? Okay. Let us say we are talking about a time T compared to time T equal to 0, therefore delta T is T minus 0, it is T, right. Now I am doing an approximate this thing, therefore I will put approximately goes equals alpha So in scaling analysis I am trying to replace the governing equation by an approximate relationship which does not involve the derivative terms, so that I get a quick understanding of the various terms involved. Okay. Delta x, now what is the delta x is the length scale, what is the length scale now for the penetration? Delta square, is that okay? What is it that I am trying to do? I am trying to get an estimate of delta. So please remember that if once an equation is given, you do not have to go to the computer straight away. So much of work is possible before going to the computer. Okay. Now if I do this, it is very interesting. Delta square goes as or delta goes as root of alpha t. So the penetration depth goes as root of alpha into time. It is intuitively apparent that as the time increases, the penetration depth will increase. As the alpha increases, that is why if some sambar or rasam is boiling and there is a ladle, you touch with a stainless steel spoon, immediately within a few seconds you will feel that. But if you put a wooden spoon, it will take a long time for you to, there it is not the K, that is the alpha. Whether at the place where you have touched, that disturbance has propagated, that is from the burner, it has come to the sambar or rasam, it has come to the ladle, and I can model it, the ladle I can model it as a one dimensional fin. Bejan has done it in his book, heat transfer book. If people are interested, you can do that. So that handle you can model it as a one dimensional annular fin or some fin or something, then you can find out exactly transient fin at what time you will feel hot. Is it okay? So this is, so delta goes as root of alpha t. Between two materials, if you want to find out the penetration depth, delta 2 by delta 1 for the same time will be root of alpha 2 by alpha 1. Okay, we can work out problems on this, all that is separate story, but the most important thing is because I got delta is root of alpha t. Suppose I introduce what is called I know from previous experience, you may ask me, sir, why did you choose 2? I can choose it as A and then I can find out the A, that is a formal procedure. Now I can introduce an eta which is x by 2 root alpha t, because the root of alpha t comes from my scaling analysis, then this eta is basically dimensionless, correct? By the introduction of eta, it is possible for me to convert the original partial differential equation into an ordinary differential equation, and I proceed. So if you use this for the early regime, this is called the similarity transformation method. Okay, let us start. I don't have enough time to do this, but so correct. Right? No, d square t by dx squared. They write it right. Okay, so what is d eta by dt? Is that correct? Vinay, is it okay? T to the power of minus half is minus half 3 1/4 huh? No, t to the power of minus half t to the power of so 3 by 2 I have taken care of, minus half I have to take care, plus 1/4. Is that okay? Now substitute and you will get an ordinary differential equation in eta. The Any problem? Why? Correct, minus.
And there is a alpha in this equation, the last equation.
What?
No, that will come in the
No. Why alpha should come here? I'm final. Alpha is coming in the original equation. Therefore, yeah, Pawan, now the alpha will come. D square t by, so what do you get? dt by t eta is that 1 by 2 alpha t can be taken out, right? You can just write it as d square t by d eta square, right hand side, correct? Yeah, you can write, isn't it? What do you want to do with that? Okay, I will have to proceed to the next. Proceed to the next topic. I do not have time to finish this off, but what will happen is I know for sure that the PD is converted to OD. Okay, so okay. Now let us leave the mathematics, let us get back to the physics. T equal to 0 or t equal to infinity, when t equal to infinity theta tends to, correct, t equal to infinity is mathematically, as far as this thing is concerned, t equal to infinity corresponds to eta equal to 0, x equal to 0 also corresponds to eta equal to 0. So by the combination of x by 2 root alpha t, when eta equal to 0 or eta is equal to infinity, you can keep the t constant and see what is happening with respect to x, or you can keep x constant and see what is happening with respect to t. Therefore by the combination of x by a very intelligent combination of x and t, we can put x by 2 root alpha t such that we will get one parameter eta called the similarity parameter, similarity variable, which will tell the whole story of the transient conduction in the slab. Okay, you will get d square t by, it will result in what is called the error function. The solution will result in what is called the error function, complementary error function and so on. I do not have time to discuss that. Now we will go to the late regime. Okay, early regime, so it is possible to do some simplification where you can introduce a similarity transformation, and then why are we doing all this struggle? Because our belief is solving ODE is simpler compared to solving PD. Okay, so if that belief is true, then it is worth doing this, otherwise you go to MATLAB and solve it, use your PDE solver and okay. For the early regime it is not required. For the late regime, okay, so late regime, so consider an object which has a mass m, volume Cp, right, h and t infinity, it is at a temperature T and it is cooling. Okay, initially Ti, it is lumped because Boyer number is Boyer number is less than 0.1, because of which I can write so this is the governing equation for the problem. I can define a theta okay. Since we are lumping it, we can't start from the original governing equation, we have to get the governing equation from first principles. I already told you the same logic we use for getting the Finn equation okay. So you can say okay. What are the units of MCP by HA? It has got the units of time, so it is basically it gives you an idea of what is the scale for time in this problem, so it is called the tau, the time constant. So now we can integrate no, is it okay? No, dt by tau, correct? So we get so for the lump capacitance system for cooling, so the temperature distribution is exponential okay. So this theta will asymptotically tend to 0 as time t tends to infinity. Okay. So if you want to do a heat treatment, you are having a stainless steel bearing or ball bearings or whatever, then if you know the initial temperature at which it is heated and you want to know and you want to pull it out at the end of, you want to pull it out when the temperature reaches 400 Kelvin, if you or 500 Kelvin, if you know that the ball bearing can be assumed to be lumped, that is spatially lumped, then you know all the properties of the stainless steel, thermal conductivity, Cp, H will be given, you first calculate the time constant, left side theta by theta I you will know, then you will find out the total time. So in your actual process, when that time is gone, you will pull out the ball bearing and continue your heat treatment process. So you are able to get a handle on this. So this will work only if the Biot number is less than 0.1. The first step is to check whether the Biot number is less than 0.1. Now what is the total energy which is transferred? Will be, what is the total heat which is lost from the body in a time t okay. So that will be q into dt, so this will be in joules or kilojoules, so this will be right, so this will be okay, this will be okay. Please look at this expression. Theta, please look at this expression that can be easily derived. Theta I is the initial temperature excess, that is T minus T I minus T infinity. MCP theta I was the original enthalpy excess of the body with respect to the surroundings. At time t equal to 0, e to the power of minus 0 is 1, so there is no energy which has been transferred. When sufficient time has elapsed such that the t approaches infinity, e to the power of minus t by tau will become 0, this will become 1, so energy transfer will be mCp theta I. So all the initial temperature excess, the body enthalpy excess is dissipated to the surroundings. So E takes on a value between 0 and mCp theta I. So from the E itself you can find out what will be the average temperature of the body during the cooling process. The average temperature is the temperature itself, but this average temperature is an important concept if spatially also the temperature is changing. Now I can complicate the problem by adding a heat generation term. It is heating, the body is heating. For example, this was the case when you are with your immersion heater problem. In your immersion heater problem, are you getting the point? mCp dt by d tau equal to HA theta, that is minus, plus Q, which is the electrical input. So there will be a phase where the heating will take place, then there will be steady state, then when you switch off the heater, cooling will take place. So you have to appropriately model the governing equation. Is that clear? So whenever you have a cooling curve, it will be like this. Whenever you have a heating curve, it will be like this. Do not ever make a curve like this. This is dy by dx, d squared by dq, everything is positive. This is called an exponential curve, exponential growth rate is unsustainable. No engineering system can, even the growth of bacteria and all that which we say that it depends on the current population, there is a finiteness in the amount of nutrients which is available. So that will stabilize after some time. So as an engineer you should not make that fatal mistake, e to the power of, you should not casually to sketch a curve like that. Some people like me can catch. Okay, fine.